Okay. So let's get started to music generation. Okay. So before I talk about this, any thought, like maybe you can share in the chat if you ever did any music generation before, any types of these kind of tasks. I mean, not necessarily neural network, but anything. Anyone has any like kind of this experience of doing the music generation? IFO on pitch. What is LFO?
So low frequency oscillator, it's about just modular synthesizer.
Oh, I see. Oh yeah. Oh yeah, I see.
More of a joke.
Oh, I think okay. Yeah, I'm not very good at that, but pure data, yes. Yeah, randomized rhythm pattern is great. Oh, low frequency oscillator. Oh yeah, so you mean music synthesis? Okay, sound synthesis. Okay, so yes, it's a little bit different type of thing. If you think about this, because in synthesis you need to control. I mean, you can control what you're generating, and you are kind of giving this full control. Like you give the input, and I design what I'm generating. But for generative system, it's more like the computer or the machine to decide what will be generated. So I think, yeah, someone said this rhythm, randomized rhythm patterns will be something. Yes, that's kind of, yeah, connected to our concept of music generation. Yeah. And if you use kind of thing like Markov chain or just 12 I mean the dice game, right? You threw a dice like and you just decide like which pitch you will play, like the 12th tone, you know. Kind of like, yes, randomized thing. Use from rock structure using touch designer and GV convert. Yes. So
It's
I think
more sonification.
what?
Well,
Sorry,
I think that the last part, the last phrase is more of a sonification of some data from rocks and stones. It's I think what it's.
I see. Okay.
Yeah, kind of.
Data
Yeah,
sonification.
Okay.
Yeah.
So there are many different ways of doing this generative system. Yeah. And you can maybe also use some kind of mapping even, right? From kind of picture or structure and map this to kind of sound structure and use that. So there are many different ways. So here when we talk about music generation, it's more like based on predictive based. So it's like I give some input, but after that, the computer will generate whatever the computer wants or the machine wants. So it's not like a control system. It's not like you are using pure data or PD or max, like you're controlling the signal all the time, right? You're controlling where it flows, where the music flows. It's like more like, okay, I'll provide you the first five notes, and then you generate maybe 100 notes for me. And this, it already depends on the training and what the computer kind of, thinks. So it's not how you control the system, but it's how you train it, and so the system understands what is going on, and this generates music kind of, automatically. So let me talk about this. So before neural network, so now everyone, you know neural network and you use neural network. But before neural network, there is also a lot of experimentation on music generation. Okay, so like what we just said, the Mozart dice game. If you know that, I mean, just throw a dice or just randomly pick some notes and arrange them together. And this is also use some random process, like someone just mentioned the random rhythm patterns. Maybe you choose a random rhythm pattern and you just repeat that several times. I don't know, like something like that. So before neural network, there is one thing. Actually, even if for neural network, like we talk about RNN, right, recurrent neural network or whatever, for this type of music generation, especially symbolic music, we also always follow the line of the language. Okay, so because there is a natural connection between music and language, and the language research is always ahead of music because everyone talks, everyone uses language, but not everyone plays music, and everyone understands language, and then this kind of linguistic language thing is always more developed than music. So for the researchers before, like they always take this inspiration from the textual generation or the linguistic, the kind of language analysis. So there is one method. This is kind of called LZ prediction tree. This uses incremental parsing. Actually, it was first developed like in last century on corpus. I mean the textual corpus analysis. Okay, so it's a statistic method. Like you have an article, let's say, and you calculate like how the frequency, right, of each word occurring, and how those patterns are formed, and then you arrange them into a tree structure like this, or some other statistical properties, and then you say, okay, now I have a basic understanding of the structure of this thing, and then I can generate my own corpus or my own text based on the structure I just learned. So it is the same idea of neural network. Okay, it's the same idea, just different in that neural network. I mean, it's different because neural network is trained, so it's different methods, but the basic, like the motivation behind that are the same. Okay, the same thing is that I have something like as this precondition, and I want the system or I want a computer to generate this for me based on the structure I learned or I get from my existing data set. Okay, so before neural network, this is mostly done statistically or by analysis. So let's say we have a kind of structure. So this is symbolic. This is the text, but it's still symbolic. And we can arrange them into a tree like this. And we can see, we can compute the probabilities of each pattern happening. Let's say, so for continuations, like, and yeah, this means like after A, B will happen with probability of 1/3, and R will happen with probability 1. So, which means if I have an R, I definitely have an A. But if I have an A, I will probably jump to B, C, or D. I don't know. So there's probability there. So this type of probabilistic or random process was the basis for most generative system. Okay. Before the neural network. I mean, for quite a long time, this was dominated for probability and statistics, and it's kind of simulates the Markov chain. If you know Markov chain, I mean there is this function, right, in max and PD. It's called Markov chain. Is how you generate things, notes or music randomly. So yeah, if you ever know that, this is something like that. Okay. Any questions? Okay. So okay, so for Markov chain, the most important feature is memoryless, right? So for Markov chain, you only have your instant memory. Like, okay, I know this node, and from this node, I compute the probability condition on this node. It doesn't have a long-term memory. It's not like, okay, I have A, B, or A, and what's the next one? So I'm always predicting my next node or next character based on the previous one, immediately previous one. So, for example, I have an A, then I say, okay, this B, C, or D. And then in the prediction is not like I have A, B, or A, and what's the next? But neural network somehow is better because it deals with this problem. Okay, how actually neural network has a encoded memory, which is written as A here. Okay, so this A is the memory unit for the neural network. So everything happened before, I will just pack them into this one representation called A. So A is my memory. So I say, oh, I have A, B, or A, and then this 4 character will be kind of regrouped into one identity, which is my memory. Then as I vaguely know, okay, something happened now, and this is represented as A, and I will input this my memory A and my new character X into the system. And then system will output a new character Y for me. So this is my next prediction, my next character. Okay. So I hope it's clear. It's like now I have access to the memory. I mean, there's problems with RNN of memory. It doesn't have infinite memory, and the memory will not be as precisely. Won't be precise. There will be a lot of mistakes. But the idea is that instead of using Markov chain or which I only have access to the previous maybe 1 or 2 or 3 nodes, now I have a kind of integrated identity as A to represent my memory, and this is more flexible, and I probably can represent a lot of structure into my memory, and it doesn't have to remember everything happened before. It only selects the most important thing to remember that's best help me to predict the event in the future. Okay, so the X is the new input, A is the memory, and this is the formula how you compute in the neural network. Okay, so my new input X and my memory A. So this is a linear combination. Okay, the linear combination, and then you use a nonlinear activation 10H. So you put this linear thing through this 10H function, and you get your new memory. So this new memory AT here incorporates my past memory and my new input. Okay, so this is my updated memory, and I can use this updated memory to generate my output. Okay, so it's the same for output. It's a linear combination here, and you put it through a nonlinear activation, which is softmax. So for those different functions, maybe let me give more explanation for what is linear and nonlinear. So for example, in this 2-dimensional planar, linear means one line. This is linear, and nonlinear like 10H, the function will be like this. Okay, so this is nonlinear. So this is 10H, and this will have a limit, right? Upper and lower limit. This will be -1. This will be 1. But this basically changes. So this linear function here, right? This line into this nonlinear activation. So this is what this does. Softmax is another function that compress your linear expression here into 0. Into the range 0 and 1. So this YT actually gives you the probability. Okay. Any questions so far? Like for neural network? Collision. Actually, the function of nonlinear activation is that if you know this deep learning, right, deep neural networks, it's actually concatenate many layers, right? So this is kind of not really shallow neural network, but if you have many layers of a neural network, and then you have one input Y, and then if you use linear function, through these layers, then this whole structure equals to one layer. Okay, because the linear layer, it has the rule of superposition. So no matter how many linear layers you add together, this is still a linear thing. That's why you use nonlinear function every layer so that you makes it like trainable. Yeah. So this is the main kind of reason why we use nonlinear function engineering. And also, this is first device because we call this neural network, right? So we want to imitate how our human brain. So this was another story of the motivation of designing neural network, is how your nerves, right, process information. And we know in your brain you use these chemical things, and this will produce the electrical signal, and the electrical signal actually have a threshold. Okay, so this in your brain, this is not continuous. It's not continuous like this. So there is a threshold. So it's either 0 or 1. So if you pass this threshold here, you get 1. If you don't pass the threshold, you get 0. So it will be something like this. Okay, so you get 0 is no activation, 1 is activation. Right, and this is definitely non-linear, and it's even not continuous. Okay, and why we use continuous function here is because we want to compute the derivative. Okay, so this is a kind of compromise here. This is not a faithful representation of your brain, and this is also like where the critics come from, for neural networks. And people say, oh, it doesn't really like imitate like your brain function. It's different. Because, if you want to compute something in this current framework, you have to make it continuous so that you can compute these derivatives here. Okay, sorry, derivatives, then you can do this parameter updating. So mostly, yeah, technical like issues, a lot of things happening here. But yeah, good question. Yeah, for linear, nonlinear functions. Okay, so this is the formula. And the idea of recurrent neural network is that it's recurrent, right? So you have from A to A, then this is one cell. And in the real recurrent neural network, it will be unfolded. If you unfold this neural network, this will be something like this, okay? From A0 to A1, and A1 to A2, until AT. Okay, so this will be a long kind of chain. When you do this, kind of unrolling this neural network. And also when you train it, you need to go back a long way. So this is what we will talk about tomorrow. So here I use these formulas. It's different, a little bit different from this, mostly similar, but there are more formulas. The reason is that if you recall our system, right, we actually have two inputs. It's pitch and duration. I mean, we have another one, this bit level, but this won't be an input because you don't need to predict the bit level in this circumstance, okay? Because every node is concatenated, and once you know the duration, you know where the node is, right, in the score. You know the duration, you know the bit level. So bit level will be some additional input, but this won't be an additional prediction. So the main things we will predict is the pitch and duration, which is two inputs. But here, in this formula, we only have one input, x. So what people usually do is that, okay, let me give you an example here. So let's see, we have 3 different types of duration, and we have 5 different types of nodes. How many combinations I can get from this?
Three power 5?
Yes, exactly. So yeah, this is a combination thing, right? I have 3 types of distribution, I have 5 types of nodes, then I can just combine them like randomly. I get yes, 50 yes, different types. And in this circumstance, we already have distribution kind of like I would say 10, maybe you're including quarter nodes, half nodes, whole nodes, dotted eighth, whatever. Approximately 10. And for median number, so the median number is usually 128, okay, entirely. But we have a range for this. We won't use every node here from C1 to maybe C9 or whatever. So in the total number of MIDI is 120 8. Let me see, it's here, okay? So you can see this number is from 0 to 127. Okay, so this is the total number of MIDI nodes. But here we have a certain range. We won't use entirely everything here. Let's say maybe we use 80 different nodes. Then how many combinations I have, right? 10 times 80 is 800. So this is actually a lot of things, because when we input this input, we will basically give this called one hot vector. Okay, what is one hot vector? Which means this input is like this, and everything is 0. Okay, everything is 0 except for one position is 1. This is called one hot vector, and this one, so this position 1, it gives the information of which combination you are choosing. Okay, so if we have 800, then this vector will be, the shape of this vector will be 800 times 1. Okay, so dimension will be 800 vector, and I only have one position, it's 1, then this 1 maybe represents C4 of duration of half node, let's see, right? And then, okay, I see. Okay, and I know this is my node, and this is how I input my divide the range into sub ranges. What do you mean by divide the range? To reduce the size. Yes, it makes sense. So usually what I will do is I will do an analysis, statistical analysis of the corpus. Okay, I think I have the code there. Okay, so, well, oh, sorry, let me clear these drawings. Let me go to, so that was not designed as my teaching material. Yeah, there should be this one. So there's a lot for data processing, really. It's not that easy to address everything in one workshop. But here I get the nodes range. Okay. What I do is I will do a statistic of the data set. So I will, for example, I have maybe 100 files. Usually 100 is too less for the neural network. You have at least 100, I mean 1,000 or whatever, or more, like 10,000 files. And then I will do a statistical analysis, and I will see which range are my nodes. Okay, and I see all, which means all my data. And then I print nodes, and I know, okay, these are the nodes appeared in my whole data set. And I know based on my data set, there will be no other nodes. Like my lowest is 36. It will be no node as 32 happening in my data set. Okay. Then I can say, okay, this is maybe the range I want to, restrict this, because for my corpus, I don't have any other node. And then image generation, I also don't want these nodes. Then I can compute the range. So the range is 36 to 67, maybe 30, 40, something like that. Okay. And this is a one hot vector. Okay, you can see everything is 0 except for one position is 1. And this is how you do. And I also do statistical analysis to the duration. And I know like these are the duration appeared in my data set. Okay. And then this will be the category of duration I will use. Something like that. So this is it's a hard kind of analysis. But if you have better knowledge, like because I know if you're a musician, you know you are using this instrument called shallow. So for shallow, you don't have all ranges of note, right? For different instruments, it definitely have different ranges. And then you know, okay, the range of shallow, maybe it is exactly 36 to 67. And then I know, okay, I'm playing on a shallow, I won't have any other notes exceeding this range. And this is another way of designing the system and, you know, knowing like what's happening there. Okay. So, okay, I'll make something like that. Yes. Yes, for velocity is more free. Yeah, definitely. You can design different ways for velocity. Usually people actually use like more kind of sparse, you know, encoding. Like for example, like we have maybe 40 different nodes, and they only give, you know, 6 different levels of the dynamics, you know, of the velocity, because for velocity number, it's also 128. Okay, in MIDI file. Okay, let me see, where is it? Okay, note on velocity here. So you can see the velocity is also 0 to 127, which means there are 128 different numbers, right? So usually people see, okay, velocity is not that important. Let me just use 6 different things to represent. Maybe 0 to 20 is level 1, 20 to 40, level 2, something like that. So they make it, you know, less numbers and make it just simpler to train. So the idea is that more categories you have, then you are actually expanding the dimension of your neural network. It makes it more difficult to train, right? I think this kind of makes sense. Like if I have a vector of 800 dimensions, then it's more likely for me to make a mistake, right? Comparing to another short vector with only 8 dimensions. Yeah, it's a probability, it's a probabilistic thing of that. And well, I mean, some people believe in the power of neural network. That's why they don't care. Like if you do this language, right? Language machine learning, you usually have like 10,000, 110,000 categories, and you just don't care. Just if you have a lot of data and you just train it maybe for, you know, one week, 2 weeks, and then you have a lot of computing resources. It depends on the condition, and then you say, okay, I don't care. Like I can have 10,000 dimension of my vector, and I can still do a real good prediction. But for in our circumstance, we don't have that large data set. For music data, it's always very few, like well-processed data set, right? And you have this limited data set, and you also have limited computing resources. Like I don't have real power GPU, I don't have that time to, you know, to train a neural network, like what the industry does. So you have to devise some cheap and clever thing to do your work that still makes it work. I mean, it won't be comparable, to industrial machine learning thing, but you still want to make your small device work, and yes, make it fit your purpose, like based on your constraint limits. That's why I somehow divided this kind of thing, which means I will separate these two inputs. Okay. So again, before we say we have 10 types of distribution, maybe 80 types of pitch, and then I will have vector of dimension 800. But now, because this multiplication is a lot of things, but now if I have two separate input, right? I have two separate input. Okay, now this one. Okay, so I have YD and YN. So D is the duration, N is the node. Then I only have two vectors, one of dimension 10, one of dimension 80. Okay, so this kind of reduced my dimension a lot comparing to this 800. Okay, 800 is a huge number in my context. So if I use this kind of pretty short, right, 10, anything like below 100 is acceptable for me, let's say. And then I have these two separate things. I don't have this scary multiplication. And then I can avoid this kind of problem of having too many categories and too less data. Okay. So this is a way of like my design of this. And that's why here I have actually it's similar things, right? Similar functions, 10H SoftBank, but I have a copy of that so that I can deal with the duration and nodes separately as the vectors. Okay. So yeah, I'll get more into detail about this tomorrow, but it's the brief idea here. And yeah, in my system now, I have two inputs, xn and xd, and I have the output yn and yd. Okay, two input, two output, and the structure is the same as this recurrent neural network. And when I generate, yeah, I basically use my output as my new input. Okay, because in this generate, I'm generating the nodes one by one. Okay, then the nodes I generate, I see, okay, this is the nodes, the next node, and this sample node will be my input. Okay, that's how I do this generation. I'm using everything I generated as my new input, and use this new input to generate something else, and then this thing can continue forever. Okay, which means if you have such a system, then you can generate a music of forever long, whatever length you want, whatever like many notes. So this is something, labor saving. Let's say you have a perfect system, and then whenever you want music, you just click one button, and the system will generate, the music for however long you want. So this is the kind of idea of the generative system. Okay. Okay. So here is one generative example of this design. Okay. So this is what we did kind of last year in the workshop, and this is one generative example of doing using this recurrent neural network and training using this solo shallow. Okay, so when I train, because I'm using solo shallow, I just eliminate all the harmonies, and I only have one monophonic line, and the notes are kind of concatenated one by one. So let's listen to this generative thing. How do you feel about this? Some computer generated music. Okay. So okay. So I'll get to the code of this. Wait. Let's see. Okay, this one. So this is the symbol strange. Okay, I mean, well, it's computer generated. It definitely has something strange, and it depends on your training, how well you train it, and yeah, things like that. But this is kind of the research idea, like how you do this automatic generative system. So here is the code. So what I basically did in this example is that I provide or I input the first node here. Okay, so the first node here is my input, and then the neural network will generate the nodes one by one here. Okay, using this recurrent structure, I know this node, I'm generating this one, and using this one, and generating this and this and this, and continuously. Okay. So as a human, as the user, I only provide the first node, okay, and I will leave everything else to the system to generate. Okay, so I actually use PyTorch. Okay, so use PyTorch to train the neural network. It's a platform for, you know, training neural network. If you know, these are my trained parameters. Okay, so I have those different parameters here. AX, AA. They may look similar because they appear here. Okay, these coefficients here. WAX, WAA, and BA, BY, etc. Okay. Print this. So I actually did the training, of course, previously. I won't train like, you know, on the fly. But these are the parameters I get. And I just load the parameter into my current system, right? And then I can just start generating. So step 2 is choose a node to start. Okay. So here is what you will do, is that actually you give the first node the node value, the duration, and the onsite. The onsite means like in which position you start playing, right? So let's say, okay, my node value is 57, maybe 55 this time, and duration is 30-second node. Maybe let's say 4. If I use 4, then it's if I use 1, it's a 30-second node. If I use 2, it's a 16th node. If I use 4, is a 8th node. Okay. So let's see 4. The onset is 24. How to compute this? Anyone can compute this. When, yeah, which position is the onset? So this everything is computed on 30-second node. Okay. So what is 24?
Two-third.
Yes, yes, yes. Very good, very good. Yeah, yeah. Yes, great. So let me see how to compute. So because it's a 30-second node, right? So if I use 2 is the 16th. If I use 4 is the 8th, right? If I use 8 is the 4th. It's a quarter node. Quarter node is a beat. And 24 is 3 times 8, right? Which means after 3 beats, I will start playing, which means it will start at the downbeat of the 4th beat. Okay. So I will make the first 3 beats as rest, and will start right on the 4th beat. So this position, this onset position, actually gives me the metrical structure, right? The metrical structure. I know the metric of this score, then I can continue, generating with my bit levels. It's just that. So let's say we choose this, and I have my duration list, and these are just some different functions, and this is my neural network. Okay, so these are the formulas I just showed you. Like this 10H, how do you multiply this? The softmax. Okay, and you use random choice, the random process, and everything. Forward step note. Okay, so this is A, this is Y. Okay. Just like I showed here. Okay, how you compute A, how you compute Y. And yeah, you just find a way to write it into the write the functions. Okay, so I'll get more into this. I write my own function, but you don't need to. I mean, if you don't want to do this, you can just use the built-in libraries in PyTorch. I write my own function because I want to have more like kind of control and design of the system, right? It makes it more like flexible. But it depends on your like ability, your programming and math level of that. Okay, so this is a generating function, and this is how I generate this. Okay, so I will output my generation as in this data frame. So let's generate. Let's see the length is 100, okay, or something, maybe 150. Generate more, which means 150 nodes. Okay, after my first node, I will generate 150 nodes after my input. Let's use this function to generate. Okay, then you can see I have 151 rows. So my first node, 55, duration 4, structure level 1 is exactly what I inputted. Okay, here, 54, 4, and yeah, the onsite. And then I generated everything, and then I use the stream to concatenate them. Okay, so this is what I get. You can see, right, my node starts at the down bit of the 4th bit, and the time structure is 4/4, and the BPM is 80 because I use 80 here. You can change the BPM. You can also change the instrument. Not really in this case. And this is what's generated. And let's listen to this in Muse score. Okay, so here you can see the time signature and BPM kind of changed. This is because when I import my MIDI file into Muse score, the Muse score has some automatic processing system that assigns the best time signature and the best kind of BPM sorry, to your score. That makes it looks like this. Actually, I think I can do better, because if I don't use stream, if I write this into the CSV file. Okay, so this is when I talk about MIDI and CSV, it's a bi-directional change, right? I can transform MIDI to CSV. I can also transform CSV to MIDI. So this is how I'm writing my generation here back to a CSV file, and then write this CSV file back to MIDI. So I'm writing everything here to my generated CSV. Okay, so open CSV, I'm writing my header, start track, tempo, time signature, etc. And then I will use the MIDI object, a MIDI writer, file writer. Okay, then I'll write my CSV to MIDI. Let's see. It's called generated. Let me find this file. Oh, it's a lot. Wow. Okay, it is here. Let me open this one. Okay, so this time the BPM is like kind of doubled, but at least the time signature is correct. Okay, it doesn't really follow my convention of the CSV, right? You can tell here in my convention of my CSV, I set the tempo, the BPM as 80, and I set the time signature as 4/4. But because it is kind of just processing problem of the notational software, it gives you what it thinks the best. Okay, it doesn't really exactly follow the convention of your encoding, but the music will be the same. Okay, your auditor experience won't be changed. Only this appearance of the score will change here. All right, let's listen to this. Okay. So I think it's a pretty successful generation, at least in my system. Okay. I mean, it definitely doesn't parallel with a composer, especially a famous composer. But I think for my computer ability, it's already good enough. But not every generation is this. Okay. Sometimes you fail, sometimes it's successful. But the good thing of this, the good thing of this system is it generates different things every time. Even if you give it the same input, the same note as input, and everything the same, and every time you generate, it gives you something different, something else. So this is what makes it fascinating. Okay, and you can always change the first note you input. And if you generate 10 times, you use the same setting, it will give you 10 different, scores that you can play, that you can use. It's kind of a composer of infinite, power. So, well, I will share this file also with you, and you can experiment with it. Yeah, but of course you need to install these packages beforehand. Like, yeah, if you successfully install these things, you can do this. And for Torch, you can just do pip install Torch. Okay, we don't need the GPU here in this notebook, so you can just you don't necessarily have to install Torch with CUDA. So you can simply use if you don't care about how your Torch will work on GPU, you can just say it pip install Torch. It's very simple. But if you want to use GPU, just Google it and say, okay, how can I install Torch with GPU, etc., etc. But in this notebook, everything is on CPU. Okay, so I transferred everything to CPU so that you don't need to worry about the GPU thing. Okay. Any questions so far? Okay, let me see. It is applied. It is applied because yeah, as I said, so this is the real score I'm generating using my system. Okay, so you can see the onset is right on the downbeat of the fourth beat. But when I output this file, I mean, if you listen to this auditory experience is the same. Okay, whether you represent in this form or in this form or even in this form. Okay, I can also play this one. You can listen to this. It's the same like listening. Wait, is it really? Is it true? It should be, right? Oh, a little bit different. I think. Oh yeah. This somehow different here. maybe probably because I use different encoding kind of ways, but sorry for this confusion. But whatever, if you read the score here, you know this is the exact score my computer I'm generating with the neural network. But the Muse score or the notational software doesn't really kind of exactly represent the score exactly. So one thing is that if you want to represent the score exactly the same way as you design this, okay, I would say, okay, I only want my score to be represented in this way. I don't want any other type of representation, even if it sounds the same. Then you shouldn't use MIDI file. You will use this thing called music XML. Okay, so I can show you this. So music XML is something. I think I open this here. So this file is music XML. This is a more larger file, more complicated, but it gives you everything precisely. Because in this file, not only the note duration and pitch are encoded, and also the position of the note appearing on the score. Okay, so this will be a huge file. Yeah, if I can show you maybe later on if I can find the resource. Then if for encoding this one note, you will need a lot of information to say, okay, where is this note? Like how the beam is positioned, how the relative position is this note and everything. Then you can just encode this precisely. But MIDI is something just it's a smaller file and it's more efficient in terms of things. I mean, for MIDI, it doesn't care about the representation as long as I give you the same kind of auditory thing. Okay. It's a good question, really good question. It's a very important problem, actually. So it will be a huge problem for people who really care about the score, the appearance of that. Okay, so maybe let's just continue for now. Okay. So time is it? See. So this is another part. Maybe let's take maybe I don't know. Take a break. It's already 1 hour, so I guess it means it's better for us to for you to take some water and relax a little bit. Let's come back like in 7 minutes. Okay, so it will be 10:35 for me. It's a very short break. Okay, 7 minutes. And let me see if I can find this music XML resource for you. I can just explain this better. Okay, so 7 minutes. Okay, great. See you later.